All right, so you can just hand your homeworks in up at the front. Okay.
Send you a mathematical file?
That'd be all right. Okay. Let's see. Okay, so let me just do a quick review of what we had. Yesterday, I was pointing out these connections between, in some sense, like the entanglement structure of the vacuum state of a CFT. So there are different ways you can consider that to be an entangled state between different regions, and some structure in ADS. And so, as a reminder, so what I said was, if you imagine global ADS, and you choose any point in global ADS, okay, and now choose, say, a particular time direction, and then orthogonal to that, you choose some plane, okay. Okay, so that plane going through that point is going to be part of some extremal surface that goes out to the boundary, and basically divides the boundary sphere into a ball-shaped region A and its complement. Okay, and then in the bulk you have and then you can think of the domain of dependence of those two regions. So this is dA and dA bar. Okay, and then in the field theory. Okay, so given that kind of decomposition, you can think of the vacuum state of the field theory and ask, well, how is that represented as some entangled state between of these two theories? And the answer turned out to be that it exactly looks like a thermofield double type state. So the same kind of state that we use to describe this maximally extended Schwarzschild black hole, where now these eigenstates are eigenstates of those are eigenstates of some particular evolution operator corresponding to a time that just lives inside one of these diamonds. Okay, so this was we had this Rindler time, this Rindler Hamiltonian, and then there was a conformal transformation from Rindler space to these diamonds, and then there's some there's something that the Rindler Hamiltonian maps to. Okay. So we basically know explicitly how to write this vacuum state as an entangled state between those two regions. And if we want, we could just write the density matrix for those two regions. Left. The entropy of these density matrices are the same, and those agree with the area of this extremal surface. Okay. And again, there's lots of there's lots of ways that you can decompose this, basically for any choice of a bulk point for any time like vector and for any kind of plane in that space-like slice defined by that vector. Okay, so there's lots of ways you can take the vacuum state, decompose it in this way, in lots of different ways. And yeah. Okay, I'm sorry. So this is okay. Yeah, it's supposed to be a zeta, I guess, a zeta or a xi. I'm not sure what I was going for there, but one of those, your favorite squiggly Greek letter, and So that, yeah, let's call it zeta. So zeta is going to be this particular coordinate that is time-like, and it lives within one of these diamonds. Okay, I'll be more specific about it later. Yeah. Okay.
Is that an R subscript on the squiggle?
Yeah. So this is like the zeta. This is the Hamiltonian that generates the zeta in the right-hand diamond, and in the left-hand diamond, and this is the, all right. Okay. Okay. These part of the notes were added at the last minute, so the rest are very clear. Okay. Okay. So yeah. So you have this decomposition, and so there's lots of ways to decompose this state into an entangled state of two things, where we know exactly what the density matrices are. And that decomposition that you have in field theory corresponds nicely to the fact that in ADS, there's, again, lots of ways to take ADS and decompose it into complementary Rindler wedges. So this bulk region that I've drawn here is a Rindler wedge of ADS, and then there's a complementary Rindler wedge. And there's lots of different ways to do that decomposition. And so there's sort of a one-to-one correspondence with how the quantum state of the CFT splits up into these thermofield double entangled states, and how ADS splits up into these Rindler wedges. And what I tried to argue last time was that you should think of these density matrices here as corresponding to the information in the respective wedges, and then to probe this region outside the wedges, you need to look at things like correlations and entanglement between the two different theories. Okay. So today, what I want to do now is go away from pure ADS. Or go away from the CFT vacuum state. Okay. So now I have a new state of my field theory. Okay. The bulk geometry, assuming that there's a dual bulk geometry, okay. So we don't change the boundary, but the metric inside is going to be different. Okay. And so there should be some correspondence between these states and the metric. And so this decomposition I talked about, I can still do that actually these boundary regions aren't changed. I can still look at the boundary, and I could still think of any pair of diamonds like I've drawn up there, and I can still ask, well, what happens? What is my new state in terms of a decomposition like this? Okay. And in particular, I can ask for any such decomposition, well, how does this entanglement change when I do the change in state? So I get one of these entanglement entropies for every one of these decompositions. And so going to a new metric would give you, or going to a new state would give you, a whole new list of those entanglement entropies. Okay. What I tried to argue last time was that, well, if you knew all of those, then maybe that would actually be enough to reconstruct the geometry. So in some sense, knowing all of those entanglement entropies would be like knowing what the state of this is. So what I wanted to do today, was kind of think about constraints. So given a metric, you could also compute all these entanglement entropies. So given a CFT, you could go to a new state and compute all these entanglement entropies. Given a metric, you could similarly compute all of the areas of extremal surfaces. Okay. And there's a really interesting point, which is that sometimes if you pick a metric and you compute the areas of all these extremal surfaces, sometimes, so that'll give you a bunch of these quantities SA, sometimes those quantities are not consistent with with those being entanglement entropies. Okay, so that's kind of the crucial point for today and part of tomorrow, that Ryuta-Kinagi, if you actually have a state and it actually has a gravity dual, it will correctly compute the entanglement entropies. But if I just write down an arbitrary metric where I don't really know that that's coming from a legitimate quantum field theory state, and if I then try to use Ryuta-Kinagi to compute extremal surface areas, and if I then try to interpret those as entanglement entropies, sometimes those will fail to be consistent. Okay, and that will tell you really interesting things about what metrics are possible. Okay. Good. Okay. So I'm just gonna draw what I just said in a diagram, so make sure it's totally clear. Okay. So the goal for today and part of tomorrow, we're going to think about this space of asymptotically ADS metrics. Okay, I drew it as a squiggle last time, but now I'm drawing it as sort of a 2D thing. But it's still much, much smaller than this space of functions S of A. Okay, so when you take any of these metrics and you use Ryuta-Kinagi, then you're going to get some function of regions of the boundary. Okay, and so I'll draw that. So this set of metrics is mapping into a measure 0 subset of this set of functions. Okay, and so what I was just saying is that there's a bunch of these functions which don't satisfy basic constraints that entanglement entropies have to satisfy. Okay, so for example, so for example, if I have regions A and B, then the entanglement entropy of A plus the entanglement entropy of B is always greater than or equal to the entanglement entropy of A union B. Okay, so this is just something that is fairly easy to prove just starting from just directly from quantum mechanics. Okay, this is called subadditivity. So I know Juan talked about some of these things. Another one is strong subadditivity, which is much harder to prove, where S of A B plus S of B C is greater than or equal to S of B plus S of A B C. Okay, and then there are constraints. One also mentioned there's this thing called the positivity of relative entropy that I'll talk about in more detail probably tomorrow when we need it. And then there's a monotonicity property as well. Okay, so there's all these different things. And so say I took a metric and I started computing the extremal surface areas using Ryuta-Kinagi for boundary regions A, B, and C, and say I found that this inequality was violated. Okay. Well, then that would be telling you that that metric really can't be coming from some consistent quantum field theory state. Okay, so you've kind of ruled it out as unphysical. Okay, so if in the picture there will be some metrics for which this happens. Okay, so these are the functions that violate some of those inequalities. These are the allowed ones. And so any metric that lands you in this region over here we would call unphysical. Okay, so what I want to do today is, okay, so ADS, pure ADS, as far as we know, is one example of a metric that lands you over here in the physical side, and actually it turns out to be right on the boundary. Okay, so this is in the physical side. And so what I want to do today is just explore perturbations away from that pure ADS. Okay, so we're just going to look at metrics which are close to pure ADS and see what do the constraints on entanglement entropies tell you about those metrics. Okay. So from the CFT point of view, what I want to do is start with a small perturbation to the vacuum state of the CFT. Okay. Yes?
Yeah, just a question about what you mean by physical. Does that just mean that it doesn't come from holographic CFT, or is there some other quality?
All right. Good question. So what I would say is, imagine you have any consistent theory of quantum gravity that has a classical limit that's Einstein gravity coupled to matter. Okay. We could talk about more general theories by generalizing Ryutake and Agi, but let's just say we're talking about consistent theory of quantum gravity whose low energy limit is Einstein gravity coupled to matter. Okay. So since this is some consistent theory of quantum gravity, and let's say so we have some asymptotically ADS condition. So we're talking about an asymptotically ADS theory of gravity. Okay. So there should be some CFT, some consistent CFT that's dual to that, right? Okay. And so if I find, okay, so any actual solution in any such consistent theory. Okay, so let's say I find a metric which is a legitimate solution in this consistent theory of quantum gravity. Well, that should be dual to some legitimate state in my dual CFT. Okay, and therefore that should satisfy all of these constraints. Okay, so what I would claim is that if you find a metric that doesn't satisfy these constraints, that it is not a consistent solution in any consistent theory of quantum gravity. Okay, so I think it's very, very powerful in general if you believe things. Yeah.
Maybe I'm just jumping ahead.
Okay.
You're about to explain, but when you say pure ADS is on the boundary, I mean, I assume these drawings are sort of schematic, of course, but do you mean like if you perturb in one way, it quickly becomes?
Yeah, I just mean what I mean is that we'll be able to perturb in some directions to unphysical things. Yeah. 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 Actually, maybe all of the physical ones are on the boundary. It's probably true that they're all on the boundary in a sense. So, okay. There's all these possible constraints, but for small perturbations, okay. So actually, there's the constraint that the only one that I know that actually gives you legitimate constraints for small perturbations away from the vacuum is this positivity of relative entropy. And I think Juan talked about this. But I'm just going to rederive the constraint that you get from this for small perturbations around the vacuum, and I'll just do it directly. Okay. So what I'm going to say now is true for any quantum system with a subsystem A. So this is okay. So this is the definition of the entanglement entropy that we're talking about. Well, now vary the state a little bit and calculate the variation of the entanglement entropy. Okay, so for that variation, we find that delta S of A, since we're working at linear order in the perturbation, so there's one term where you get delta rho times the log of your original density matrix. And there's another term when you vary the log where you get like 1 over rho, which cancels this one, times a delta rho. So there's another term which would just be trace of delta rho. But rho is something that always has trace 1. So trace of delta rho vanishes for any perturbation. So in fact, this is the full answer to what the perturbation looks like. Okay. And now we could rewrite that a little bit by defining this thing called the modular Hamiltonian. Okay, so the modular Hamiltonian is just the logarithm. So it's an operator. It's just a logarithm of the unperturbed density matrix. Okay, so whatever state you start with, there'll be some density matrix for this subsystem A, and then this is just some operator. Okay. So then we'll just make that replacement in this formula. And you get this. Okay, so now we have a statement that the change, if I start with a state and I vary the state, the entanglement entropy changes by an amount which is equal to the change in the expectation value of this modular Hamiltonian. And this turns out to be useful if we know what the density matrix that we started with is. Okay, so if we actually have some useful expression for rho, then we might have an expression for h, and then this thing will have some useful content. Okay. Why this equation is true? Okay, so I'm taking the definition of S, and then I just make a variation. So delta S is equal to trace of delta rho times log rho, plus another term which is trace of delta rho. And the other term we set to 0 because trace of delta rho is always 0. Because density matrices have trace 1.
So you have that time trace rho weight times rho weight.
Yeah. So the other term would be rho a, trace of rho a times the delta of the log rho a, which is going to be 1 over rho a times delta rho a, so really it's just the 1 over rho cancels those and then so it's really just delta rho, trace of delta rho. You need to, I mean, you might be worried that there's some ordering issues, but actually if you do it carefully, you find it really just is just delta rho. Okay. Let me give you an example where this should be very familiar. Okay. Okay. So, and we're still in a very general quantum context. Okay. So let's say we just take any quantum system, which is in a thermal state. Okay. So here's your favorite quantum system. And it has some Hamiltonian. And so in the thermal state, the density matrix is this one that I showed last time. Okay. And so in that case, if we plug, so then the modular Hamiltonian is equal to beta times h minus log of z. Okay. And then if you plug that into here, what it gives is that delta SA says if you vary the state from that thermal state, that the change in the entanglement entropy is 1 over T times the change in the energy. Okay. And that's just the first law of thermodynamics. Okay, so this is like dE equals TdS. Well, it's not really. So usually when you think about the first law of thermodynamics, you're thinking about perturbing from some equilibrium state to some nearby equilibrium state. And this is thermodynamic entropy. But interestingly, there's a first law of thermodynamics that holds at the quantum mechanical level exactly for any perturbation to the density matrix. And that's this. And it says that the change in the entanglement entropy of the state, even if I perturb to a state where ordinary entropy wouldn't be well defined, you can still calculate entanglement entropy. And the change in the entanglement entropy is 1 over T times the change in the expectation value of the energy. Okay. So this is like a quantum first law of thermo. Okay, any questions? So that's true for any quantum system, and now we want to specialize to conformal field theory on Minkowski space. I could do a conformal field theory on a sphere like I was doing over there, but this is physically equivalent by some conformal transformation. Okay, so we'll just do a conformal field theory on Minkowski space, and I want to see what this first law tells us for this case. And in this case, I'm going to start out where the state of my conformal field theory is the vacuum state. Okay. And I'm going to take A to be a ball-shaped region. Okay. And so again, this is going to be useful because if you remember, taking A to be a ball-shaped region and talking about the vacuum, this is a case where the density matrix, again, actually has the form of a thermal density matrix. Okay, so we're actually going to be able to compute the modular Hamiltonian in this case and get a useful formula. Okay, so I'll just review that a little bit because we didn't really last time we talked about a ball as being part of a sphere. Here's a ball as being part of Minkowski space. But it's still true, the thing we used last time. Okay, so it's true that there's some conformal transform that maps the domain of dependence of that ball-shaped region to this Rindler wedge of Minkowski space. Okay. So there's a conformal transformation that maps from here to here. Okay. That's a geometrical statement. Because we're talking about a CFT, okay. So the vacuum state of a conformal field theory is conformally invariant. And so when I map from here to here, back and forth, if I'm in the vacuum state in this picture, I'm going to be in the vacuum state in this picture. Okay. And so what I'm going to use is that I know the density matrix for this Rindler wedge. Okay. And then I could just take that density matrix and map it, use my transformation, and that will tell me what the density matrix is in this region, or for the ball. Okay, sorry. So that was time. So in this case, what I said was the density matrix is exactly the thermal. Okay, so there's this Rindler time coordinate, which is generated by the following. It's generated by the boosts. So explicitly, that generator looks like T delta x plus x delta t. Okay. And in that case, I could write, okay, so that's the classical transformation. This h is just the quantum operator associated with that. Okay, and so that I get by the usual methods. Okay, so I'm basically just end up replacing the del t by t0, the t00 operator, and the del x by t0i. But actually, this is okay. So I'm writing the form of this Hamiltonian on the surface t equals 0, and then this term goes away. Okay. Yeah, just to make it absolutely clear what I'm doing, I mean, so, you know, if you talk about a quantum field theory and you say, what is the Hamiltonian? Well, there's this time translation symmetry, right? And then you can work out the conserved quantities associated with that symmetry, and then there's a quantum operator that generates that, and you get that by integrating the zero component of the current. And so that's okay. So in the usual case, this is the Hamiltonian, and now we're just saying instead of this symmetry, we're looking at another symmetry, which is the boost symmetry, and then there's, you know, you do the Noether procedure, and this is the generator. Okay, and so that's what I mean by this density matrix. When you map it over here, so all that happens is that first geometrically that symmetry, so that flow gets mapped to this one. Okay. I could write down. Actually, I probably won't write down. So there's some specific in these new coordinates. There's some specific form of exactly what does that flow look like. So there's some vector field that generates this time flow within this wedge that's the image of that time flow. And then I just go ahead and write down the quantum operator that generates that one. Okay, and it looks like this. So H. I'm going to write this somewhere else so you can see it. Right. So this is going to be important. Okay. Yeah. So we have this ball. There's some particular time-like coordinate I can define in there. And this is the thing I was calling zeta before. And the quantum operator that generates that looks like this. Okay, so it's kind of like the ordinary Hamiltonian, where you'd integrate the stress, the T00 over all of space, except now we're just integrating it over this ball with radius r. And then there's some function of r that we're weighting it against. So this function goes to 0 at the boundary. Okay, so this is something this is an operator that's naturally defined within that ball. Okay, and so then the density matrix So our goal was to figure out what is the density matrix for this ball. And you get it by taking this density matrix for the Rindler space and making this transformation. And then all that happens is that H Rindler gets replaced with this H. And so the density matrix for a ball is, again, of this thermal form. Okay. So that's good, because then we could just use our quantum first law of thermodynamics. Okay. And so in this case, the modular Hamiltonian is 2 pi h sigma minus log of z. And so we just plug that into our first law. And you end up with this statement. Okay, so this is the result that we're going to use, and this is a statement that's true for any conformal field theory. So exactly what we're saying here is that if you start in the vacuum state of a conformal field theory, and you consider any perturbation to that state, and you consider a ball-shaped region A, then to first order in the perturbation, the change in the entanglement entropy for that region is actually going to be equal to this quantity involving the integral of the stress tensor. Okay, so that's some constraint on the entanglement entropy. Actually, we'll see shortly that the stress energy tensor can be related to the entanglement entropy for infinitesimal ball-shaped regions. Okay, so really, you could express this as entirely a constraint in terms of entanglement entropies. It would say that the change in the entanglement entropy for a ball-shaped region, you could actually figure out by looking at how the entanglement entropy for infinitesimal regions changes, and then doing some integral. Okay, so that's the nature of that constraint. Any questions? Yeah. Exactly. So we started in the ground state. That was important because we wanted to be able to compute the density matrix for the ball-shaped region explicitly. So if I'm in any other state in a CFT in higher than 1 + 1 dimension, I don't know how to compute the density matrix. Okay, even for the thermal state. In 1 + 1 dimensions, I can compute I might be able to do more. I could compute the density matrix for a thermal state for an interval. But in general, this is what I could do. Yeah, so that's very special. Generally, the modular Hamiltonian for some region in a field theory is not going to look like the integral of some local operators. It would just be some enormously complicated non-local operator living in that region. And we can't say anything about it. Yeah? So this is, again, the squiggly Greek letter that I chose to represent something like a time coordinate that lives within the domain of dependence of the ball-shaped region A. And so this was, so this was the thing that, so there's a coordinate in a Rindler wedge that is generated by boosts. Okay, so if I'm, so there's a, right, so it's like the time for an accelerated observer. Okay, and then I just make this conformal transformation, taking the Rindler wedge to this space. and that time maps to this coordinate theta. I mean, I could write it down in terms of the other coordinates, but what I've drawn here, this is just like the flow of the vector field. So these are, yeah. Right, which includes balls, and yeah. Yeah. So that's exactly right. So basically, balls. That is all. You could, and half spaces, which are already what we started with. So. Okay. Yeah. I mean, I think people have talked about perturbing. There may be some universal things that you could do if you just perturb a ball a little bit. I've seen some discussions of that, but yeah, so there may be a little bit more that you can do sometimes. Okay, all right, so now I want to specialize to holographic CFTs. And actually, when I talk about holographic CFTs here, there's precisely one thing that I'm going to assume, and so we don't really need to assume anything, very much of the ADS CFT dictionary or string theory or anything like that. I'm basically just going to assume the following thing. So when I say a holographic CFT, I mean this in a very, very weak sense. So suppose that we've found some CFT such that for a family of states psi near the vacuum, that there are geometry that the entanglement entropies of these states are represented geometrically. Okay, so we assume that we found some CFT so that there's this family of states where I could associate dual asymptotically ADS geometries such that the entanglement entropy of this state is equal to the area of the extremal surface in this dual geometry over 4g Newton. And actually, all I need this to be true for would be ball-shaped regions. Okay, so I want to make that assumption. And notice that I'm assuming I'm assuming this particular form of the Ryu-Takeyanagi formula. Okay. One thing I didn't really dwell on is that there are examples of ADS CFT where this thing is going to be more complicated, and I think Juan mentioned that, where you could have some higher derivative terms here, and that would correspond on the gravity side to having like higher derivative gravity. So the context that we're imagining this is ADS CFT, where we're talking about Einstein gravity coupled to matter as the classical limit. But yeah, so this is all I'm going to assume. And so this, because we're talking about states close to the vacuum state, this geometry that computes those entanglements should be close to pure ADS, which computes the entanglements for the unperturbed state. Okay, and I'll write down a specific form for those perturbations. Okay, so this is Pfefferman-Graham gauge in which ADS looks like this. Okay, and then being asymptotically ADS means that the corrections start with this power of z and then have only higher powers of z. So h mu nu of z comma x. And h is something that is well behaved as z goes to 0. It goes to some constant, or it just goes to some function of x. It doesn't blow up. Okay. Okay, so our question is, so supposing that this formula works, and given that we know this to be true for all CFTs, what does that tell us about H, about this perturbation? Okay. Okay. So the first thing I'm going to do is actually convert this into a statement which is purely about entanglement entropies. Okay, because if we just look at, so far this has this expectation value of the stress energy tensor. And I don't really want to assume the ADS CFT dictionary. So, knowing ADS CFT, we know how to relate that to geometrical quantities, but I don't even want to assume that. I'm just going to assume this. Okay. So the first thing I want to do is just understand what this is telling us. And so I do that by trying to apply that constraint for a small ball, an infinitesimal ball. Okay, so here's my tiny little ball in the CFT, and that should have some corresponding extremal surface in the dual geometry, which is going to be localized quite close to the boundary of our asymptotically ADS space. Okay, so I'm going to start with the right-hand side of that. Okay, so and I'll call that delta E. Okay. So this side is defining to be delta E. Okay. Okay, so delta E for this little ball of radius r. And I'm going to be looking at the limit where r goes to 0. And according to that, that should be equal to delta S be in the limit where r goes to 0. And then using our assumption, I can convert that to a geometrical thing, which is the delta A of B tilde over 4g Newton, also in the limit r goes to 0. Okay. And now if we look at this expression, okay, so in the limit r goes to 0, all it's going to depend on is the expectation value of the stress tensor at that single point. Okay, because your ball is now zooming into a particular point. And so you can just evaluate that by Taylor expanding the stress energy tensor expectation value about a point. And then you find only the first term actually contributes to the leading behavior of this integral. Okay. So what you end up with is some constant times some power of r times the stress tensor at some particular point. And then on this side, also what you get is that the change in the area, that's really only going to be sensitive to the metric close to the boundary and also close to this particular point x0. Okay. And there's some calculation that you can do to figure out exactly what is this. And what you end up with is that it's equal to this, the I component of this function h. Okay. So this function described the metric perturbation. So this little change in area, it turns out at leading order, all it depends on is, sorry, again, there's an r to the n. All it depends on is that particular metric component, the trace of the spatial metric at x0 and in the limit where z goes to 0. What is n? It's an integer, which is in my paper, but it's somewhere between 0. Well, it's yeah. So I'm sure it's between minus infinity and infinity. So no, it's just some. I could work it out, but it's just let's see. When you do this integral, so you get it by doing this integral. Can someone quickly do that in their head? It's r, and the answer to this integral over this ball is r to the n. Yeah. Okay. Is c times r to the n. Yeah. So you do that integral, you get c times r to the n times just the leading term in the Taylor expansion, and then on the right-hand side you find the same power of r, and so those are just going to cancel out. Okay. And so what you end up with, what you learn out of all that, is that delta t00 is equal to some constant times hii, z equals 0, okay, where the x-coordinate is the same on both sides. This is not a very covariant-looking formula, and that's because I chose a ball. I chose some particular spatial slicing. I was looking at a ball in this slice t equals 0. So I could get a covariant version of that. Okay, so we worked in the frame of reference associated with some time, some velocity vector for an observer, which is just in the time direction. Okay. So this kind of defined our frame of reference where we took that ball. And what we ended up showing was that delta t00, and I'll write that in a slightly more suggestive way, is equal to h00 minus eta 00 times h mu mu. Okay, so that's what we ended up showing, which is equivalent to saying u mu u nu delta t mu nu is equal to c u mu nu. Okay. Okay. So working, choosing this velocity vector to define our time, or this time-like vector to define what are we calling time, we ended up deriving this equation. But then I could just do the same thing for any time-like vector, okay? And I would, again, get this equation just with the other u. So this is sort of the covariant version of what we just derived. So this is true for any, because this is true for any time like u, it follows that this tensor equation also has to be true. Okay, and in a conformal field theory, on Minkowski space, this trace of the stress tensor is going to vanish. Okay. So we actually learned two things here. So that tells us that the trace of this Okay, so that tells us that the trace of this function h at z equals 0 has to vanish. Okay, so that's actually our first, you could think of that as our first constraint on these dual geometries. So you can't just choose any old h there. For the h at z equals 0, the trace has to vanish. Okay, so I can actually get rid of this term. And so then the second thing we learn is that delta t mu nu. The second thing we learn is that for any CFT with this property that some of its states have entanglement entropies computed by dual geometries, the expectation value of the stress tensor in the CFT is equal to the this particular the z equals 0 limit of the metric perturbation defined that way. Okay, and so this is actually a standard element in the ADS CFT dictionary that is derived in other ways, but this is showing that you can just get it directly from Ryu Takenagi. Okay. And actually, it turns out this is really powerful because if I started with a more so this is totally an aside, but in other examples of ADS CFT where the dual gravity theory would be some complicated higher derivative gravity, then this element of the ADS CFT dictionary is not really known in complete generality. People worked it out for various examples. But this gives you a method to derive the dictionary between the expectation value of the stress tensor and some geometrical thing, some gravity thing in kind of an arbitrary theory. Okay, and so we did some examples where we rederive things that people had done in different ways, but also you can do some very general formulas that hadn't been worked out before. Okay. So going forward, the main thing that we're going to use this for is now to so using that, the right-hand side of this formula is now geometrical for any. So now what we did so far is use this for little balls. Okay. Now we're going to use it for arbitrary size balls. This side was always geometrical based on our assumption, but now we've made this side geometrical. Okay. And so now we're just going to get a completely geometrical constraint using that. Okay. Any questions so far? Okay.
This is just one component of the GKPW dictionary. Can you get the rest in the same way as there in all the other fields?
Yeah, that's a really good question. I feel like you should. I mean, especially since at least some of it would be related by supersymmetry, or. So. Yeah, I feel like, and later things I'm going to say also, like getting linearized equations. So I feel like there could be some, you would need something that generalizes entanglement entropy, but maybe that thing exists. I feel like there's something to be done there. Yeah. Okay. All right, so now we just want to do the same thing, but for general balls. Okay, so our CFT statement again is this. Okay, but now using this result that we just derived, I can write the right-hand side as something involving the asymptotic metric. And so I'm going to replace t0, 0 with this constant times h0, 0. Actually, it'll be convenient for... so I could either write hii or h0, 0. And here there's like an x, and we're at z equals 0. OK, so this right-hand side now is this integral. And the left-hand side, using our assumption, is the area b tilde over 4g Newton. OK, and that you can actually rewrite in a simple way as well. OK, so if I want to change... OK, so see, I have this extremal surface in ADS. And now I want to now I change the metric. OK. And I want to figure out how does... so I want to, in principle, now compute the new extremal surface in the new metric, and then compute the area of that new extremal surface. OK, so I need to compute area of x plus delta x in the metric g plus h. OK. And so, and delta x is also going to be order h. So we need, like in principle, you would need both corrections because you're changing the metric, and also corrections because you're changing the surface. OK. But the great thing is that because the surface was extremal in the original metric, OK, the condition for it being extremal is that the first order variation vanishes. OK. So the good thing is that if you're just working to linearized order, you can actually ignore that change in the actual surface. And you could just compute the area of that original surface in the perturbed metric, and then it's way easier. Okay. So that, it turns out, then just, so that's a fairly simple calculation. Actually, OK, this is your homework. So this is a good thing to try. So you've just got this. You've got this surface, and then you change the metric, and just compute the change in the area of that surface. And you can see the answer is really simple. So the calculation is not too hard. OK, so we have that equals the integral over b. This is an integral over b of something involving h. All right, so basically we've got b and we've got b tilde, and now we have translated our CFT statement into something which is just a constraint on this metric perturbation h. It says that if you integrate this thing over b, it better be equal to the integral of this thing over b tilde. B function of h equals b tilde some function hat of h. And so if you just picked an h out of a hat, it's unlikely to satisfy this. OK, so we already see that we're going to get something that constrains what h we get. OK, and notice that this isn't just one constraint. So there's not just one thing to check here. There's a separate constraint for every single ball that we could choose. So must be true for all b. OK. And So I've already kind of argued that the set of these balls. Actually, at the beginning of the lecture, I kind of indicated that there's, in some sense, like a one-to-one correspondence between points in ADS, and so you choose some point in ADS and some frame, and then we can associate a ball to that. And so it's sort of plausible that maybe we actually have enough constraints that the set of all these constraints could be equivalent to some local constraint in the bulk. Okay, and that's what we're going for. I mean, so this is a constraint. It's a bit ugly. It's hard to know like exactly what is that telling us about H. So I want to convert it into a nicer form. Okay. And it turns out that you can do that. So so I'll just tell you the nicest way to do that. And so this is very much like taking the integral form of Maxwell's equations and trying to figure out some local equations based on those. So we're going to end up using Stokes' theorem. And so the way this works is that if you work hard enough, you can find a differential form that depends on which region you're talking about and the metric perturbation. Okay, so there's this particular differential form that you can write down. It's a little bit complicated, and I won't write it down explicitly, but it's just something that is linear in H and derivatives on H. Okay. But the properties that this form has are that if you integrate it over B, so you integrate it over this boundary ball, you get this thing. And if you integrate it over the B tilde in the bulk, you get this thing. Okay, so the integral of the form over the B is the delta E. The integral of the form over B tilde is equal to the other thing. And the other thing that we're going to use is that the exterior derivative of the form is some positive function times, this is the TT component of the Einstein equation, of the linearized Einstein equations. And then there's the volume form on sigma. Okay. Okay, so how does this help us? So we just use, this is our starting point. Okay, so delta S okay, so this is like the main argument, and it's only 3 lines, so good time to open your eyes. And so I just use those first 2 properties to say that this is equal to this equation. Okay, and so this is the same thing as saying that it's the same thing as saying that the integral over the boundary of sigma is equal to 0. So looking at this picture, sigma is the spatial region between b and b tilde. The boundary of that is you could say b minus b tilde. And so saying that the integral of chi over the boundary of sigma vanishes is the same as saying this is equal to this. Okay. All right. Now we use Stokes' theorem. So that implies that the integral over sigma of d chi is equal to 0. Okay. And then we use the fact that this d chi is equal to this thing which involves a component of the Einstein equations. Okay. Do I want? Okay. Okay. Sorry. Another bracket. Okay. Yes. Okay. Okay. So this. Okay. So this is a separate thing. So we had this non-local constraint. Okay. And I wanted to turn it into something local, and so I was trying to use similar machinery to how you might go from integral to differential Maxwell's equations, which is basically Stokes' theorem. Okay, and so yeah, I mean this is a bit of So here I'm just asking you to accept the fact that there exists such a form. And the reason why I'm looking for it will be clear in a second. So if I find such a form, I mean, right now we can say suppose there exists such a form, then this is equivalent to this, which is equivalent to this, which is equivalent to this, which is equivalent to this, and that has to be true for all possible regions sigma. Okay, so the integral of this thing has to be 0 for every possible region, right? And then this turns out to allow you to conclude that this is possible if and only if this particular component of the linearized Einstein equations is satisfied everywhere. This step is slight. There's actually a couple of steps here because this function here actually is not the same function for every sigma. Okay, it's not immediate that has to be 0, but there's like a couple of lines of argument that allows you to conclude that the only way for this to be 0 for all possible sigma is for that to be 0. Yeah, I mean, so just as a historical, so how do you just think of introducing this form? As a historical note, so we had this. I mean, I guess based on, I think various previous work, specifically of Jacobson. So Jacobson had this old work where he had somehow gotten Einstein's equations out of something that looked like the first law of thermodynamics. Okay, and then Myers and Cassini and Huerta Blanco and Hung, Blanco, Hung, Myers, and Cassini had written down this precise sort of first law of entanglement. Okay, and so going in, I thought, well, maybe you could get the Einstein equations out of that, or linearized Einstein equations out of that. And so you can do work, and this part is easy. You write this down, and then you stare at it and say, well, okay, is that Einstein's equations? And then I thought, yeah, okay, is there some form? Maybe you could do something like this, and so I was working with a graduate student, and we tried to write down some differential form for a while, and And that wasn't working out. So then we just used brute force. So at that point, we just took this and Taylor expanded it in R, in the size of the ball, and then took the Einstein equation thing and Taylor expanded that and kind of checked by brute force and eventually by some induction proof that it was exactly the same thing. And it was really only later, so in the second iteration, after conversation. So, I'm going to talk. Okay, so I'm going to talk about where some of this formalism comes from tomorrow. But so this form is something that comes up in Wald. Wald has all these fancy ways of talking about gravity and how to derive laws of black hole thermodynamics. And so this form is actually something that comes up in his formalism. And so in the second iteration, once we were aware of that formalism, we realized that was exactly what we needed. And then later, just as an exercise afterwards, now that I knew there was an answer, so with Wald's formalism, it's extremely difficult to actually go from the formulas to what is this thing equal to in a situation that you want. So it turned out to be easier to actually just derive that form based on these properties. Okay, so you can actually, if I just tell you to go home and as homework exercise number 2, find a differential form with all those properties, you'll work for 2 or 3 hours and you'll get the answer. Because you just try everything, you just write down a general thing, which is linear in H and first derivatives of H, and put in those constraints, and then you get an answer. So yeah, it kind of looks, it's very, very streamlined here and magical, but as usual, there's a bunch of, it took some work. So you shouldn't be afraid to just use brute force if necessary. If the thing you're trying to show, if you can't find a nice way, just try to use brute force, and you'll convince yourself that it's true, and then later you'll figure out the nice way to do it. Yeah. No. Yeah. So I should have said that. So we're not assuming that the bulk theory is pure gravity. We're just, again, all we're assuming. We're not even assuming that the bulk theory is anything, but we're just assuming that there is a geometry that computes these entanglement entropies. And so the linearized Einstein equation, if you take a gravity coupled to various matter, the stress tensor for the matter is typically quadratic or higher order in the matter fields. Okay, so when you're just talking about the linearized equation, it actually really is kind of universal. Okay, I'm short on time, but yeah, I'm clearly almost done. So, okay, so. Yeah, so we got that, we took this CFT property that I just erased, and our basic assumption allowed us to recast that as a constraint on these metric functions, which is non-local, and then we did some mathematical wizardry, thanks to Bob Wald and his collaborators, to convert that into a local equation, which was the TT component of the linearized Einstein equation. And so we already did, I'm going to just use now the same trick that I used earlier in the talk. So when we derived we would derive the TT component of the holographic stress tensor dictionary. And then I said that was because we started in a frame of reference associated with the time-like vector 1, 0, 0, 0. And then I go through and just redo it in a general frame. And I get that delta, that all of those components of the Einstein equation are satisfied. That's actually still not all of the components. So there's still these components, which are known as, these components you can think of as what gravity people call constraint equations. And so what that means is that if these are it turns out if those are satisfied at the boundary, then they're satisfied everywhere. And so all you need to do is show that these are satisfied at the boundary. And this one turns out to follow from the tracelessness of the stress tensor. And this one turns out to follow from the conservation of the stress tensor. You just take this, use our newly derived formula for what that equals to in terms of the asymptotic metric, and then you end up getting those. OK. OK. So the summary was, we just thought about metrics which were close to ADS. We assumed that there is some dual CFT, so we assume there's some CFT state for which those metrics are computing the entanglement entropies. We used the constraint that exists for entanglement entropies at linear order perturbed away from the vacuum state, which is delta B CFT equals delta E CFT. And then that allowed us to first get a gravitational constraint that was non-local, and then we showed that that's exactly equivalent to the linearized Einstein equations. Okay, so the summary is that if you have a CFT state whose entanglement entropy is computed by some geometry close to ADS, then that geometry has to satisfy the linearized Einstein equations. Okay. The other summary in the context of, let's imagine any consistent quantum theory of gravity whose in the ADS CFT context, we imagine that there's actually some full, like here we haven't really assumed that there's some full theory of quantum gravity dual to our CFT. We've just assumed that there are these geometries which calculate the entanglement entropies for you. Okay, so in ADS CFT, you have more structure. You assume there's actually a consistent gravitational theory. And in that context, I guess what we've done is seen that this linearized Einstein equation, which should follow from some kind of CFT physics, actually follows from this entanglement first law, together with Ryu Takanagi, which is the only element of the dictionary that we need to assume. Okay, so I'll stop there, and I'll talk more tomorrow about the walled stuff and where this comes from. Okay. Yes. Yeah, I'm going to talk tomorrow about, so today was one step away from pure ADS, and tomorrow we're going to take 2 steps and then a hop. And so we'll get, so it turns out, and this is stuff that hasn't been published, there's a nice thing that you can say at second order as well. So I'll tell you a little bit about that tomorrow. And then there are things that you could try to say using these entanglement constraints, just generally speaking, without assuming that you're very close to ADS. But I'll save that for tomorrow. So it really just assume for a family of states psi near the vacuum that there exists a geometrization of that entanglement information. And so that probably, it's not, you just pick a CFT, it's not going to be true. There's no, so presumably this is only true for CFTs that actually have gravity duals. Let's see. What do you have in mind specifically? Yeah. Actually, okay. So this is related to the right. So basically, your question is which So here, this is some special class of CFTs. So one thing you could do is say, okay, well, given that assumption, can you convert that into something more useful in CFT language, like about the spectrum of states? Or can you convert this assumption into something else that would tell you more about which CFTs actually have those properties? And I think that's a really interesting question. I'll probably mention a little bit about a way that you might try to do that. Yeah, it was connected to some of the things I said yesterday, like how given that, right, you don't need, if you want to deduce a metric given a state that you think has a gravity dual, you only need a limited amount of information. So if I want to deduce what is given this, if I'm given the expectation value of the stress tensor everywhere, well, then I could just solve the linearized Einstein equations and figure out what the metric perturbation is. But then the entanglement entropy for any other region better match the computation that I would do in gravity. And that's going to be a constraint. And maybe you could massage that into a useful form. Yes?
Earlier you were saying that the Takayama formula could kind of be derived from ADS safety and Einstein equations. Like, to the extent that it can be derived. And then now you can derive Einstein's equations from it.
Wait, sorry. You mean? Are you talking about Maldacena-Lukowicz? Yeah. Okay. All right. So So, So the approach I took today was just to take this as the only thing I'm assuming, and then kind of get Einstein equations. What Maldacena-Lukowicz is let's see. So what did they assume? I mean, they kind of assume an ADS CFT correspondence where the partition function in the field theory matches some gravity partition function. And what else did they assume? So they probably assume that gravity, that there's a classical limit, so that gravity partition function for any boundary conditions would be dominated by some particular saddle point. And so they assume kind of the standard kind of ADS CFT dictionary between the partition functions, between the field theory and the gravity thing, and then they can derive this in some context. Yeah, we should have coffee. Yeah. Do you know what the plan is for tonight specifically?
I'm just going to go talk to Tom.
Okay, yeah.
Eva just canceled during your talk.
Oh, okay.
But, I think the rest of us are up for it. Alex, my wife, is going to come.
Okay, all right.
But yeah, as of lunchtime, there wasn't a restaurant yet. So
Okay, all right.
it says.
All right. Okay. Yeah, I'd be up for anything.
Okay.
Actually, yeah. Unfortunately, did Eva cancel to play soccer? She didn't do that.
No,
Okay.
she said she